Hello there, thank you for joining me again today. On the bench for repair from a radio amateur who's asked me to look at this for him is a Marconi 2955. It's actually known as a 2958 because of this add-on at the bottom, this additional module. This is going back to the days when we were testing cellular phones here in the UK on the analogue system before GSM came in. There was two systems that came in originally in the 1980s and was used right into the early 90s before GSM came in. There was TACS and then there was ETACS. TACS was 600 channels and it worked at 900 megahertz insofar as the mobile phone received, and then the mobile phone transmitted I think 35 megahertz lower, about 800 and something megahertz. And TACS was expanded in the late 1980s to ETACS, which stood for European Total Access Communication Systems. That's what TACS stands for. But the E version of it had 1329 channels, 1329 channels. And it's basically the module at the bottom here had the software in it to configure the test set for TACS and ETACS, and indeed it also carried the signalling standards and the encode, decode and the auto test features that you could do with mobile phones as an ATE environment, automated test equipment environment, and it would produce a pass or a fail limit on each test of audio, TX power, receiver sensitivity, cyanide. It measured all that automatically, and then you will get a printout from the parallel port here as a conformance test QC check for the customer, and that naturally after you carried out a test or repair on an analog mobile phone, then you would give them the printout from this service monitor so that it will prove that the repair was successful. And obviously as the years went on, GSM came in the early 1990s, and then these became redundant basically because obviously this test set can't test GSM, and the add-on module at the bottom only did TACS and ETACS, analog cellular. Now interestingly enough, there is another version of this add-on at the bottom called the 2960, and it had little panels here, and basically there's a set of UV EPROMs inside. It's the same shape and model of tray as this, except it had options. So one of the options was ETACS, and then the other options could be like special signalling standards such as MPT1327 Trunked radio networks, and then other standards like paging standards and various other systems that you could buy, and military systems as well for particular types of data signalling and such like that the NATO military would use. And so you could purchase different options for the bottom tray, and then obviously you could expand the system capability into other radio networks as well. I think over in Norway and some parts of Europe in the sort of 1990s 80s used their version of mobile phone technology, which was similar to TACS or ETACS, but I think it was like the American version, AMPS, and other types of network that they're using over there with their own unique signalling standards. So Marconi made a tray that you could just fit different UV EPROMs in software that you ordered, and it came in a little box, and then you just bob those EPROMs in the tray, and then it would obviously adopt that software standard. So yeah, quite a unique little unit. Obviously these two connect there, and then when you turn this on, which we'll show later on in the video after we've repaired this, that you could then go into the auto test screens and test various parts of cellular mobile phone functionality. Now the gentleman who's brought this to me for repair says that it fails self-tests. So if we go to the self-test screen and run the self-tests, and then we should be able to let it run through its checks. Now I've got it hooked up already to the spectrum analyzer for later when it's just run through these tests. and we'll have a look in the manual in a moment as to what these tests mean and the error codes and what they're about, and then we'll do some checks to see whether there's anything in particular that stands out. So at the moment it's just failing those first 5, which is test.1.0 to 1.4 with the error code that's displayed. All the other tests seem to be functioning, passing, so that seems to be okay. Now just increase the intensity. So yeah, it looks like it's got to the bottom of the screen without failing anymore. Okay, so test.10, 1.1, 1.2, 1.3, 1.4. So if we look at the manual here, we've got some information as to what these tests are. Now, basically this is test 1, which is highlighted here at the top. There's different sheets for different tests, and basically, here we go again, Adobe. Not interested in Adobe. What do I want Adobe Flash Player for, you know? Right, so we've got, it says test.1.0, 1.1 for example here, frequency 0 fails, high frequency, 1.2 low frequency and frequency 0, and frequency 1, etc. Now if we look down here, frequency 0 is 20 megahertz and frequency 1 is, I think it's 111 megahertz, yeah. So it's telling us that those two frequencies there, it's failing on, and which seems strange, but anyway, we can have a look at that. Now, one of the first tests that I'll do, if I just come back in again, is we're going to link the output of this service monitor to what is the HP8920 spectrum analyzer, radio tester with the spectrum analyzer on. I want to see whether it's a fault on the transmit side, i.e. a signal coming in where the frequency counter section may not be working, or the RF power section may not be working, so it can't read in its self-test mode what our signal generator is producing. And I also want to see if it's producing an RF signal out, seeing as the fault code shows that it's not passing the tests on certain frequencies. So what I'm going to do is I'm going to go into receive test. I'm going to set up a receive test measurement here. We'll do RF gen frequency, and we'll just set that at 111 megahertz, 111 megahertz. We'll set the RF gen level to neg 40 dBm. We'll leave it there. We've got the RF coupled out here, and then on the HP8920 we'll just go into the spectrum analyzer. We'll just move this over into the spectrum analyzer port, and then what we'll do, we'll see whether this is producing a frequency output. So we'll go back to main on the HP8920. We'll set the center frequency as 111 megahertz, and we've got a signal there. Now if I move a marker to check the level, because obviously if the level's wrong that may also flag up an error insofar as the software, it's minus 40 dBm, which correlates to what the Marconi says it's giving out, which is obviously neg 40 dBm. Now if I adjust that with the variable control and we increase that, say, to neg 30 dBm, and then check the level again on there, we are again getting neg 30 dBm. It's a bit difficult on this camera until I get right in there. So we're spot on. So it is producing a frequency and a level that's correct. So let's check it on 20 megahertz, for example, which is test frequency 0 according to the technical information that we've got. And then go back to go back to main on here, select center frequency, 20 megahertz, and yes, so we've got again the level that we're giving out here is neg 30 dBm, and what we're recording on there is also neg 30 dBm as well. And there we have it. So it looks to me like as if, well, we'll check the other frequencies. So we've done 20 megahertz, 111 megahertz. Let's do 300 megahertz. Megahertz at neg 30. Again, go back to the main, center frequency, 300 megahertz. Yep, neg 30 dBm. Yeah, reading neg 30 still. We'll do 400 megahertz next. Center frequency, and we could put the increment on actually. Increment set 100 megahertz, and then all I've got to do then is just press the up button instead of entering it in manually all the time. So that's 400 megahertz. I'll set the increment on this Marconi as well to 100 megahertz, and then we can just go up then in increments. Right, press that again, and then that again. So that's 500 megahertz. Then we'll do 600 megahertz. That's still reading fine. 700 megahertz. Yeah. 800 megahertz. So going up in increments of 100 megahertz. That's there. 900 megahertz. That's there. And then the highest frequency on this test set, which is 1 gigahertz. And we've got a level there as well, which is the same as what it's showing on the front of the test set here, the RF level output. Now if I adjust the RF level as well, and we keep an eye on what we've got there, we'll just adjust the marker so that it's actually on. Oops. Marker. We'll just adjust it so it's on the peak. There we are. Back to main. Right. Okay, so I'll adjust the level now on the Marconi 2955. So we'll put minus 40 dBm in. Oh, let's have a look here. Minus 40 dBm. So that's minus 40. I'll set the increment on that as well to be 10 dBm steps, or 10 dB steps. Right. So that's minus 50, minus 60, minus 70, minus 80, and then we're into the noise floor there, minus 90. So we're going up in level now, so that's minus 60, minus 50, minus 40, 30, 20. So that's as high as we can go on that port. So we can see that the levels are correct. So I don't think the issue, the frequency stability as well and accuracy of the test set is spot on, because we can tell that with the frequency we've entered in there, it's not shifted off so much. So it's not a frequency error issue. So I think we'll now need to look to see whether it's the transmit monitoring side of this test set which has obviously failed. Now what I can do with that is I can set up the 8920 to give a signal out, and then basically what we can do then is we can generate a signal out of that into here to test whether the TX side under the transmit side works. So we should see frequency, power and modulation as well, so we'll check that next, because if the frequency counter is not working or the TX monitor side is not working, then naturally it won't be able to do a self-test either, or pass any self-tests. Okay, so now we've switched to the transmitter test. We're going to inject a signal into this port now to see whether the test set picks anything up. We've set the Hewlett-Packard test set here to generate a receive on RX test to generate a signal out at 20 megahertz at plus 18 dBm, which is quite a high level. So we should really be picking something up on here. And I can't see anything there. It's not trying to lock onto anything. Now if I put in the TX frequency, just in case the level's a bit too low for it to lock onto, and you have to, for auto tune, put the frequency in. Ah, right. So we're getting something now, though the frequency offset's saying it's best part of nearly 20 megahertz off frequency. It's reading a power level of 10 milliwatts. It's a frequency of 20 megahertz, but yet the auto tunes doesn't seem to be picking that up. If I go back to auto tune, it's not reading the frequency. Okay, so what we'll do, we'll move this port over now, just in case the sensitivity of a test set on the high powered port is too much attenuation for the frequency counter to read at the level I'm giving in. We'll move it onto the high sensitivity 1 watt port, this BNC. So we'll flick over to that. We'll just disconnect this RF connector here, and we'll just gently push it onto there with it being an N. Right. So now we've got the power reading still, but yet no frequency. So let's just enter the TX frequency in. We'll put in 20 megahertz, and yet it's still saying it's off frequency by 19.9 megahertz. So it looks like the RF power meter is working. We've obviously injecting, I've got a deviation of 3 kilohertz I think coming out of the HP Agilent test set, and we're reading a level 3 kilohertz FM deviation. If I put the scope on, we can see as well in the scope if these buttons work. Yeah. Let's have a look. And we can move a position as well. So that looks okay. So I think it's down to the frequency counter board. So we go to auto tune. Even when we put the manual frequency in, it's not locking on either, and on auto tune. So we'll try a different frequency on the test set here. We'll try. We'll leave the amplitude high, and we'll set it at 100 megahertz. Let's see if I can do it. Right. That's interesting. It says it's 500 megahertz there. Am I putting the wrong frequency in? No, definitely entered 100 megahertz in. So I think it's got 100 megahertz. Let's go back to transmit, see if it'll log on. I think it's got 500 megahertz. Let me just re-enter that frequency in again on there. 100 megahertz. It's definitely 100 megahertz it's giving out. So the frequency counter is working, or it appears to, but at only 24 microwatts. So it's not reading the correct power at that frequency anyway. So it looks to me like the frequency counter power meter section for the IF, because it reads RF power from the IF, it might not be locking onto the frequency properly. So let's do TX frequency 100 megahertz, and let's see if the power changes when we enter that frequency in, and it does, 23 milliwatts. But yeah, the offset's way off again. So I think we've got a problem with the frequency counter board, RF power meter board, that looks at the TX frequency and the RF power. So I think that's where we need to start looking. We'll try duplex test, and then it'll be a single port for duplex. We'll just see whether we've got anything there. We have 24 milliwatts again. So I could try different frequencies and see whether it locks on, but I'm fairly confident that, yeah, if it's not going to lock on at 100 megahertz, it's not going to lock on at any other frequency, is it? So I think we'll start getting into it now and having a look in the unit itself and the service manual and go from there. Right, we've disassembled it now. We've taken the tray off the bottom. It's basically the top of the test set is on the bench, and this is the bottom section. We removed all the screening cans ready to do test and measurements on the various boards on this side. We have got the can off the back where the power supply is encased, and like any electronic equipment, doesn't matter what it is, the best place to start is with the power supply section. Check the output voltages from the power supply first to correct. No use delving deep into the other part of the system unless you can check that the power supply is functioning to start with, because you could lead yourself off down all kinds of garden paths looking into different circuits and the way they operate and trying to diagnose faults that may be phantom faults caused through the power supply voltages not being correct. So let's start with the power supply and we'll measure that. Now, according to the circuit diagram of the power supply, which I've expanded here because it's quite an in-depth diagram, we've got various voltage rails coming out. So we've got a plus 12 volt, a minus 12. I think that says there plus 35 volts, which I think is used for the yeah, plus 12, minus 12, plus 12, minus 12, plus 5 and minus 5. They're the output voltages. So that's what we need to pick up off this circuit board. Now there's one of the wires is connected down here. There's a little post which is just down there. I'll just zoom out a little just so that I might be able to get a bit more definition on it. So there's a post there next to D24. There is a post here as well. Then the other two wires come all the way down, and there's a post just down there. It's quite difficult to see, but might be able to get a bit more light in. There we are. So we've got one of the wires, the white and orange stripe goes down to this post, and the red is just there. Now that's the more difficult one to measure, simply because it's next to this post for the screening can to connect to, and it's quite easy to short that out to that terminal to that post, so you've got to be careful measuring that one. Bit of extra caution. Right, so we'll use the Fluke scope meter to measure these, and we'll check for any AC component on them as well, a high frequency component as well as DC. And if need be, for 5 volt rails out of adjustment, we can adjust it with this blue potentiometer, and then we can see if the fault lay in the power supply first, and then progress into the rest of the system. Okay, so we're clipped on now. We're ready to rock and roll, and let's see what we've got onto here. We switched the test set on. The fan's whirling round there, so we're good to go. So it's just a case now of going on this probe and seeing what voltage. So we've got plus 5 on that post, which is correct. We'll have a look at this post down here. There's a post just beneath there. If I can find it, I can zoom in, just see whether we can find it. Because we've got this white wire disappearing off down there. Let's have a look. There's a terminal just there next to this post. You can probably just see it. It's a real pain to get to that because it's so close to that this post here, you know, so you can short it out very easily. So again, you know, you have to be careful. Bit of a silly place to put it, mine, but there you go. Right, so what we'll do, we'll carefully try and get onto that, and we'll see what we can get to. Let's just go in onto there, and then let's see what we've got. Right, so we've got minus 5.2 volts. So that takes care of what is the white and black stripe wire and the red wire. The next one is buried deep down here again, near that post where this capacitor is, but just for ease we'll just go on to this one just to see what that one's like. Again, you've got to be very careful. So we've got minus 12 volts. So then I surmise the other one that's near this capacitor is actually plus 12 volts. So we'll have a look, see whether we can get on that. I think that's going to be quite an interesting one to get onto as well, due to its close proximity to that that post. Again, bit of a daft design. Right, let's have a look, see if we can get onto that. Right, and we've got plus 12 volts there. So we now know that the power supply is functioning correctly, and then we can start looking at the other modules inside now to do some fault diagnosis there. Right, so we're down to the technical description first, the functional description of the board and how it works. But basically, before we look at the description, the signal that's coupled in from the RF attenuator section, which is for the front RF sockets, it eventually arrives at this board. This is the RF counter board, before it then gets passed off via this link here, an RF sample that comes in here through this attenuation, this teledyne relay switched in and out, this pad, and then the attenuation goes out then to another attenuator, diode attenuator, which then's mixed, and then this is a demodulation board. This deals with the basically the IF for generating demodulation for AM, FM and phase mod for transmit measurements. So first of all, signal comes into the frequency counter board, and then the digital output's fed out on these. The RF signal's then coupled through then into this board for the demodulation of a TX signal to take place. This board here is the signal generation for the signal generator, and the synthesizer and VCO circuits are all under these cans. And then the other board here is the output RF amplifier section and 200 MHz oscillator for sub-frequencies below 200 MHz. It mixes signals together with a signal coming in here to generate the signal down to 400 kHz. And also we've got the RF amplifier hybrid amplifier stages there before that's passed off to the RF attenuator, which is on the other side, which then feeds the RF signal generator output to the 20 dB pad, which is where the TX signal comes into as well. So that's how you get the duplex. Now it says in the technical description, it says that the RF input and outputs are connected to the RF in-out BNC and N-type sockets. For the BNC socket, the input is sampled on AC2 board, and if excessive power is detected on AB1 board, the input is isolated by AC2 in order to protect the signal generator. No such protection is required for the N-type socket since it is directly connected to a 20 dB pad. Excessive power at this socket results in overheating, which is sensed on AC2, causing the detector on AB1 to inform the microprocessor, which flashes a warning on the screen. For excessive RF power at either input, an audible warning is generated from the audio amplifier AB1. It says this warning overrides the voltage control on AF2. The changeover switch on AC2 responds to the select key for the simplex operation and defines the signal path for one port and two port duplex operation. Signal generator output from the RF synthesizer is via a 10 dB attenuator on A4 and then via a 100 dB attenuator, which is switched in 20 dB steps by drivers on AB6. Signal input is fed from the splitter to the modulation meter on AA1 and to the RF counter on AA2. The signal to the counter is fed via a 20 dB pad to a prescaler, which is switched in for frequencies above 200 MHz. The counter is gated, depending upon frequency range, by the divider on AB4. The resulting frequency measurement is fed out on the data bus to processor board AB4. Now, if we have a look to see whether there's any more information regarding that. Oops, we jumped. Let's see if there's any more info. So we've got the block diagram appearing of how that's fed, and I think then we can look at the actual signal measurements now as per the block diagram. So we've got RF in out, we've got an isolate input switch, changeover switch, and then we've got duplex simplex select, and then we've got then going to the splitter, the mod meter, the prescaler, the high speed decade counters, and then going into dividers, low speed decades, and then off to the processor control. So we'll have a look at this circuit diagram now for this PCB, which is the RF counter, and then let's have a look doing some measurements around this board to see whether we're getting the division that's should be as per the diagram. Right, we've got the schematic diagram now for the RF counter section, and as we can see there, we've got what is the RF in coming in, switched in via this relay here, various pads, attenuation, more attenuation, then we get it fed into what is the 16 dB amplifier. Again, potentially here we could have, if I can just zoom in a bit, we could have a supply issue problem here. We could have insufficient signal coming in for this particular amplifier to amplify, and thus then feed off to the other parts of the circuit. But there's all sorts of different things. If we have a look up here as well, there's an enable line from going across here. If I just move the diagram across, we'll see if I can find the mouse cursor a second. Just move it across, then we've got a DC switch up here, and so we've got a 5-volt rail being fed to the board here, permanent, and then we have a switched input, and this prescaler and bypass switch, power switch, we need to have a look to see whether this is switching as well and feeding supply off down here as well as off to other parts of the circuit. Potentially there could be component failures in this area, but then we'll look and see what we get with regard to signal amplification there. We'll see whether we got the signal coming in. We'll use a spectrum analyzer to look at the side of this capacitor to see whether we've got the RF spectrum coming in to start with, but it's not an issue with the attenuator relays or the pad prior. We'll probably measure the signal here and then there on the input to see whether it's it's losing anything significantly, and then we'll measure the signal there and compare it to the output here to see whether we can get any RF signal that's been amplified before we then deal with this stage of the circuit. Okay, so we've got further description now on exactly how the RF counter works fully in a detailed level. So let's have a look at that. Now it says that the RF counter is a standard gate counter which has a divide by 4 prescaler switched in at frequencies above 200 MHz. Normally resolution is to 10 Hz. Below 200 MHz the gate time is 100 milliseconds. Above 200 MHz the gate time is increased to 400 milliseconds to compensate for prescaler insertion when 1 Hz resolution is selected. It says 5. The prescaler switching and gate timing are controlled by the processor, which notes the frequency, checks that there are 3 successive counts which are the same, and then sets up the counter chain accordingly. Now there's a 20 dB pad which is formed by this relay and these resistors here, and it basically says about that, it says the signal from the front panel RF switch is connected by the signal input line to a 20 dB 50 ohm pad formed by R3, R4 and R5. It says this is switched in by the processor when it detects that the power input has increased to a level where the sampling gate on AA1 is approaching a nonlinear condition. The pad also attenuates the input to the counter and avoids overriding the input amplifiers. It is switched in by RLA controlled by the 20 dB in-out line to TR1. It says when the line is taken too low, TR1 is switched on and the pad is inserted into the signal path. The following 50 ohm splitter formed by R6, R7 and R8, which is these after the relay, has a 6 dB loss in all directions and splits the input between the RF counter and the sampling gate on AA1. It says regarding input amplifiers IC1 and IC2 provide a 10 dB per stage gain, which restores the signal level lost in the splitter and matching circuit, as well as providing an overall gain for the signal input to IC3. IC3 is both a limiting amplifier and a Schmitt trigger. It has positive feedback from output pin 3 to input pin 10 to ensure Schmitt operation at low frequencies below 100 MHz. This is necessary to drive the following dividers with the correct slew rate at higher frequencies. Sine wave operation is acceptable and the high gain is not required. D6 across the amplifier input acts as a peak detector, with C12 and R13 in parallel with IC3 internal impedance as its time constant. This keeps the amplifier from self-biasing under high signal level conditions at high frequencies. So as for the prescaler and counters, it says here from IC3 the signal is routed to the divide by 10 counter IC7 directly or via a divide by 4 prescaler IC6. The routing for this is switched by TR2 given from the divide by 4 divide by 1 line at TTL levels. A low level switches on the prescaler, a high level bypasses IC6 via diodes D2 and D5. The first 2 counter decades are provided by IC7 and IC5. IC7 is an ECL divide by 10 BCD binary coded decimal counter with a gate facility on INH pin 6, pin 16 and TTL compatible inputs. The gating signal of either 100 milliseconds or 400 milliseconds duration originates in the programmable counter on AB4 and is applied on the gate input line to TR3. TR3 with IC8 level shift the signal level from TTL to ECL for the following counter. IC7 pins 2, 7 and 8 and 10 are state lines and pin 11 is the carry, i.e. divide by 10 output. The output from pin 11 is inverted by TR4 to ensure correct polarity for IC5, which is a TTL divide by 10 binary coded decimal counter. The state lines are from pins 8, 9 and 11 and 12. Pin 12 is the divide by 2 output to the next set of dividers formed by IC4. The signal at test point 2 is thus either frequency in divided by 80 or frequency in divided by 20 depending on prescaler setting. So that's something we'll look at in this measurement as well, is using test point 2 to check that. The state lines from both IC7 and IC5 are taken to IC4, which is a 7-element counter. This IC has internal registers which store all 7 of the internal BCD binary coded decimal states plus those of the external counters IC7 and IC5. The resulting data is read when enabled by a low on the EN enable counter line to pin 20. When the internal registers are addressed by the processor on pins 14 to pin 17, the data is read from the tri-state outputs on pins 1 to 4. Note that the data bus is not exclusive to the counter but is shared with the synthesizer in the modulation meter. Overflow information is provided by an internal latch which, when addressed, makes available an overflow flag. At the end of the counting period, a further address clears all the internal counters to 0 and outputs a reset high pulse from pin 19. This resets the external counters IC5 and IC7. So that gives us a little rundown of what this does. So we'll use the information provided in that technical description on test point 2. Now I think test point 2, if I'm not mistaken, I've seen that somewhere. It's one of these little it might be on this board. I'm going to need to find out where TP2 is, and then whatever frequency we give it in, we should have that divided by 80 or 100, whatever, as it says. But we'll have a look at that, see whether test point 2 actually is on this board. So that's the next thing to look at, and then we can do some frequency measurements and see what's actually happening. Okay, so we found test point 2, which is on this frequency counter board. We've got the probe connected up, and we've connected the ground cable lead there to the screening can. We've got that connecting up to the Rigol scope, and I've done auto on that, auto ranging. Now, interestingly enough, we've got the input signal connected in here from the 2968 radio test that we're injecting 150 megahertz in at plus 10 dBm. Now, if I look at the screen, it is demodulating. If I switch the carrier on, we have got the demodulation, but if I can move that out of the way a second, it says 149 megahertz off. Auto tune doesn't work. It's reading power but no frequency. We're getting the mod. So I think what we've got there, even if I put in TX frequency and then entering 150 megahertz, it's still showing 149 megahertz off. Now, if we look at the oscilloscope, there's nothing coming out on TP2 at all. Now, interestingly enough, there's something quite strange happens. If I just zoom in on that a bit further, so at least we've got something that's a little bit better viewable for you, because this camera's not very good at focusing at the best of times. If you keep your eye on the screen, when I switch the RF carrier off, when I switch it back on, you can see it's just trying to do something. So that's a carrier on, carrier off, carrier on, carrier off. It's trying to produce an output, and it's not working. It's trying to fire, but it can't quite get there. So I think what we'll do, I'll probably put the scope probe in on this test set, and we'll start looking at the higher frequencies, the actual RF frequencies that are coming in on this through this pad after this relay, and then going on to there. I'll probably go on to there to see what levels we've got there too, but we've definitely got something strange going off. We've got a hybrid amp down here as well. Might just measure some supply voltages, because that's quite cool, is that hybrid amp, and they normally run quite warm. So might just start measuring some voltages, some DC voltages first as per the diagram, and then start measuring some signal levels just to see whether or not we've got any you know, anything that stands out, like DC volts not getting to some of the chips, etc. Okay, so we're ready now to do some DC measurements with the probe. So we'll have a look round and see what we can see. So on there I can see on this switch here, I can perhaps go on to either side of that transistor, which will be the top side of it will be R22 with the look of it, onto the top side of that 5-volt switch. So we can perhaps find that on the board, R22. Let's have a look. See if we can find it. R22. If I can just find that. Right, I've got R22. So I'll just move that out of the way a second. So R22. If we can just get the camera to focus, it's playing up today. Here's the camera. Let's see if it'll focus. There we are. So R22 is this resistor there. So I'll just get onto it. Just have a look on there. Let's see what we get. So we're getting 4.7 volts. And then on the other side, which goes to the base of the transistor, we're getting plus 3.9 volts, and it's a NPN, so PNP rather, so it's switched on, if that's the case. So we should be getting supply, according to that, on diode. If I can get it to focus, should be getting supply on these diodes here, diode 3 and diode 4. So let's go to that side of diode 3 and this side of these capacitors and see whether we get any. That would be I think around about here, if I'm not mistaken. Let's just have a look here, see if we can focus. If we can focus in on it. Let's have a look here. I think the diode's around about here, diode 3. It'll be the top side. It'll be the top side of diode 3. So let's just get onto there. Let's just measure onto there and see what we get on the meter. 4.5 volts. So that means then the IC, this IC is getting supply from that transistor. So let's go to these amplifiers now and see if we can pick up an RF signal coming in on there. Okay, as per the diagram, these two amplifiers here each have 10 dB of gain roughly. So what we're going to do is we're going to go on to these capacitors. C1, we're then going to go on to C5, which is straight after IC1, and then we're also going to then look at the output of IC2, which is C9. So in regards to this, this here is the first capacitor we'll go on to, C1. That particular capacitor couples the input to this IC1. The output goes via this capacitor here into the input of IC2, and then the output of IC2 goes through this capacitor here. So we'll look on the spectrum analyzer. I've got my probe ready to go on to what is the input, and then we can measure the signal levels as well while we're at it. Right, I've just got to try and work wonders while I'm holding a camera as well as trying to get on the test point as well. So basically on C1, on the input here, we have a signal level, which I believe is neg 49 dBm roughly. So I would expect to see on the output of that module 10 dBs higher. So let me just pull that probe through again, because the cable's getting caught up. And then this time we just need to go onto this capacitor, which again is a pain in the backside trying to get onto it. And that will be, we'll go onto this side of a capacitor if we can get on it. Let me just get the probe on it. It's very difficult. Trying to hold the camera and do all this at the same time is nigh on impossible. Right, so we're on the output now of that module on that capacitor, and now we're getting, or was getting till it slipped off. Now we're getting a gain. Now it's plus 40, 39 dBm, so minus 40. So we've got a 10 dB increase between the input and the output. So what that tells me is IC1, the IC on the left there, is working. So that's that stage. So now we'll go on to the output, which is C9 on IC2, to see what we have there. So on the input to IC2, we have that level, minus 40 dBm. Now if we go on to the C9, that's what we've got on C9. So we've got a lot less coming out than we've got going in. So that's the input to IC2, and that's the output from IC2. Now in comparison, if I go to the input to IC1, which I'll do using the magnifier, because of my eyes I can't see the damn print on the board without the magnifier. Right, so that's the input to IC1, that's the output of IC1. So as you can see, there's a marked improvement, and that's also the input as well to IC2 there, and then the output of IC2 is there. So it looks as though at this stage we need to check the supply voltage to this IC, but that IC2 there has failed. This OM345 module, which is made by Philips. So we've got on pin 4 on that IC the allegedly 12 volts DC, which I'm going to check next. But as far as the RF conditions are concerned, it's not actually working. But this one is, and that looks like it's been replaced before that OM345, because this looks like as if it's a newer module, or in comparison to this one, this looks older. So we might have an issue here where we have to purchase an OM345. Now what we can do as well is I can inject a radio signal directly on pin 5 from the signal generator and have a high output level on it to see whether the rest of the frequency counter works, and that will tell us if this module is the actual fault as well. It'll localize it to that. So we'll measure the supply voltages next and see what we get. We'll just see if the DC conditions on IC2 are correct. So we'll get our probe and we'll just go on to pin 4 very carefully, and as you can see there, we've got 11.92 volts. So that proves that the IC2's got supply getting to it. So it's not a DC supply issue, so I'm quite confident that module has failed. But the next plan is to attach a coax to what is C9, which is just above it, this capacitor here, and see whether we can inject a signal of sufficient amplitude from the radio test set, either one of these, or signal generator, just to see whether we can get the frequency counter to work, because then that would rule out any other IC issue or other problem that there could be on the board. So that's what we'll do next, and then once that test confirmed that it is still reading frequency properly when we inject a signal on the output of this of a high amplitude, then we know the rest of the frequency counter is working. So then we just need to replace this hybrid amplifier. So I shall be back shortly. Okay, so we just while we're awaiting the part to arrive, we've just been cleaning the test set because it was very dusty on the front and dirty on the inside. We've going to put some fresh air filters in here. We've dusted this out, vacuumed it out, cleaned it with foam cleaner, same with the power supply cover that's inside there, and all the filters will get replaced as well. We'll put some new air filters in. But I noticed another thing as well, which you might be able to see on camera. When you press the TX button here, if you watch the whole keypad, it's difficult to see it, but basically you can see the whole, as you press a button, the whole keypad's moving inwards in this top corner. Doesn't so much happen here in this sort of area to the right, but certainly on the left, it's, you press a button there, you can see the keypad moving in and out. Might be able to see a bit better there, but it's definitely got a lot of movement on the PCB, so whether screws are loose or what, I don't know. But anyway, when I look inside, if I just move this round a bit, you can see that just about where is it? Just about here. Seeing if I can get it on camera better. There's a screw there, and obviously a screw here, but the screw on the far right is missing. So there's no actual screw holding. So obviously when you do that, you press the buttons in on the front, the board's moving. So we'll have to put a screw in there, and then also down there I think the screws are there as well further down. So it does look okay. Now I haven't found the spare screw. That screw, if it's dropped out in there, I haven't found that. So I'm going to give a test set a good inspection internally by moving it from side to side, seeing if anything drops out, looking obvious place where if it's dropped right down there, you know, that's exactly where it's gone, if it has gone down there. So we'll see if we can find that, if it hasn't dropped out. So yeah, we'll bob a screw in there, and then at least that stops the keypad from freezing up. But so somebody's obviously had a, unless it's just got loose and dropped out over years, but I haven't found it in the bottom. When I had the bottom cover off to you know, do maintenance in the bottom where we were earlier in the video, there was no screws dropped out there. So I'm a bit worried about that. We're going to have to try and find it, see whether it's hidden somewhere. I don't want it shorting something out or whatever, so we'll do a few knocks and what have you, and try and route round in between the RF tray at the bottom and the motherboard to see if it's knocking about inside anywhere. Okay, so where we're at now is we just need to check the gain of the RF amplifier stages on the frequency counter board. Now we've got, if I just move this light over here a second, we've got some hybrid amplifiers on the board, OM345s, which are, if I can find them in a moment, let's have a look. There they are, there's two of them. There's this first one here, that OM345, and then there's a second one there. Now at the moment we're injecting a frequency into the front panel here from the radio test set that we've got up here. If I just zoom out, this radio test set's producing 100 megahertz at 0 dBm into the front socket there. That's obviously been distributed around inside and obviously to these amplifiers. Now what we're going to do is, because the frequency readout's not working, we're going to do two things. we're going to check the gain of each amplifier to see whether both amplifiers are faulty or just one. We're then going to, following that, we're going to check the DC conditions, and then we're going to inject a frequency directly onto the output of whatever amplifier's failed to see whether the frequency readout works, and therefore we can pin it down to that one single fault. So what I've done, I've set up a lead, which we've got here. It's we're working on quite a low VHF frequency, so it's not that lossy. If we were going to use UHF frequency, then obviously this would be quite lossy. So I've chosen 100 megahertz as a roundabout low frequency figure. We've got that coupled off now to the HP8920 radio tester with the spectrum analyzer set up to 100 megahertz on the input socket here on the antenna port for sensitivity, high sensitivity measurements. Now what I'm going to do is I can just show you briefly on the diagram that we've got two amplifiers, which as you can see there, that's what this board is, the frequency counter board. So the first amplifier is what I pointed to start with, which is on the left, and the second amplifier is on the right, and they both give, according to that, a total of 16 dB gain, so roughly 8 dBs per amplifier. So what we're going to do, we're going to check first of all to see the signal condition, then we'll check the DC conditions. They work on a plus 12 volt rail with the look of them, so that's what we'll look at next. So if I just briefly, if I just go on to the with my lead a moment, just move this round. So let's have a look here. So the capacitors down here, these little black capacitors that are on the board there, they couple the RF in, and then there's another one there which couples the RF from this amplifier to that amplifier, which is this capacitor. Now after it comes out the second amplifier, it goes through this capacitor. So we can either get on the legs directly, or we'll get onto the capacitor. So let's just check the input to this first amplifier. I'll just slide this down there, the earth. We've got the earth lead connected, or the braid of the coax connected to the metallic screening can. So we'll just go on that section first, and we can see we've got a signal there, and according to that, it's got a gain, whatever it says there on the right on the level. So that's the input level there. Now if I just hold that onto the input of that pin and see whether we can get a decent gain, we sort of you can see it's sort of middle of the screen, and then on the output then it's quite significantly higher on the first amplifier. So then going into the second amplifier is that level, but then coming out of a second amplifier is that level. So we've actually got a loss. So if we go back onto the input of the amplifier again, we've got that's on the second stage. On the output of that second stage amplifier, we've got that. So we've got a significant loss on the on that second stage amplifier. So that's definitely not working. So I think now it's time to measure the supply voltage on it and see whether the DC conditions are correct, just in case the amplifier's got a loss of power supply. And then I've got a replacement OM345 to go in, so we'll have a look at that as well. So I'll be back shortly. Okay, so we're now on the supply rail pin on the OM345 down there. and we're actually getting 11.92 volts DC, so that's about right. So I think that means then basically that we can more or less say this ON345 module has failed and it's time to replace it. So we've got a replacement which is in this box down here, and so this is the replacement IC, the bond equivalent for it, which has come today. So we're going to insert that in, and hopefully it'll get it working. But before we do that, I'm just going to do an experiment now where the output of that amplifier there is fed through various dividers, pre-scalers, and then the frequency read. So I'm going to actually inject a frequency on the output of that amplifier, basically onto that capacitor there, and we're going to see whether we get a frequency readout on the front. Now, if I turn the mod on this test set, I'm generating a mod frequency of 2.5 kHz at 1 kHz 2.5 kHz deviation at 1 kHz. We're actually getting that on the test set. So if I turn the volume up, for example, and just increase the, where is it now? You've got to set the frequency right. I've got that set at 10 megahertz. So frequency 10 megahertz, and that should then get it to do that. That was it. It was 300 megahertz was the test frequency we were using originally when we started doing all the tests. So if we go to transmit, and we do if I do TX frequency, and then enter in 300 megahertz, 300 megahertz, and now we should be able to demodulate what's coming in. There we are, look. So I know it's upside down, but basically we've got 2.5 kilohertz deviation, and that's what it's reading here as well. So we know it is just the frequency counter section and not the demod section or the RF power reading section that's failed. It's just a frequency readout, that's all. So if we press auto tune, you see it can't work out the frequency. So that's why we've obviously got to repair that amplifier. So what I'm going to do now is I'm going to inject a frequency on the output of the amplifier. Now I'm going to do that is I'm basically going to switch that off. We're going to go on to this test set now, and I'm going to set this up so that that's producing a frequency of 300 megahertz down this coaxial cable to this probe here. We're going on the output of the audio of this RF amp onto this cap, and then we're going to see whether it reads a frequency on the front. That's what we're going to do now. Right, we now set the test set up here in RF gen mode, so it's generated a 0 dBm signal at 300 megahertz down this coax. We've got the frequency counter just in auto tune mode at the moment, just sat there. So if I touch this little probe onto this capacitor down here, I've just got to be careful I don't touch anything else. It's right. Now we've got a frequency readout, you see. TX frequency 300 megahertz. So it's reading the frequency, which proves that the frequency counter components beyond that amplifier are all functioning correctly, as they should be. So that proves that that works. Now if I were to remove that, obviously it loses frequency because I've just taken the probe off. But if I enter on their TX frequency and then put in 300 megahertz in, that will tell us if the accuracy of the oscillator as well as the stability of the frequency counter is correct, because we've entered a manual frequency in at 300 megahertz, and I've just entered an extra digit in there and then press the megahertz key. There we are. So it's on You can select auto tune by pressing that, but it's on manual tune now, entered in 300 megahertz, and the offset should be displayed here. It's displaying 299 megahertz offset. If I reintroduce this this probe again onto the output of this capacitor, then you can see that, and then the offset's just 770 Hz, which is the difference between the oscillator in this test set of mine, and we'll do an adjustment on that a bit later when we've replaced the IC. But you can see there that it's fully functional now, and of course if I were to press the auto tune button as well, if I just press that for auto tune, and then now go on to that probe, if we go like that and touch it, then you'll see that it'll tune to 300 megahertz. There you go, look, automatically, which is a frequency that's coming out of my signal generator. So the next stage now is to remove this board and replace that IC, and then we'll come back. Right, so we've got the board out now from the test set, and one thing I've noticed is that the amplifier that's failed here, which is this IC here, this one, that looks like it's not been replaced before, but interestingly enough, its neighbouring IC amplifiers has been replaced before, because somebody who's done it hasn't cleaned the flux residue off the board. Now, I think they've reworked or replaced these two ICs as well on the board, but they haven't cleaned off the flux residue, so I'll clean that off as part of the repair process. But that must have failed originally to start with. Perhaps whoever on the test set prior, the gentleman who's given me this test set for repair, I think this belonged to a company that he had, and it may be that they did send it away for repair at some point in the past, and that's why that IC got replaced, and this may have been okay, but now that one's failed, because that's the one that we're going to be replacing. So yeah, interesting how there's been a previous repair done on that board. So we'll get it replaced and then put it back in, and the next thing you'll see will be us injecting our signal in the front to see whether the frequency counter works as it should do. Okay, we've installed the new IC now, which is just here. This can locate it again. I've just lost it. Where is it? Oh, there we are. Look, that's it there. So it's been installed. That's the new IC there. So that's the replacement for the OM345. That's all been nicely soldered in, and then we've got the old one out here, which has been removed. No obvious sign of failure as such, but anyway, we've connected it up again to the radio test set. We've got the coax coming into the high power port. We're generating plus 10 dBm on the other radio test set, so I'm just about to switch the carrier on. We've put the frequency at 300 megahertz, and let's see whether it auto tunes now and comes up with the right frequency. So I'll switch the carrier on now, and there we are. So it's finding the frequency, and so that just demonstrates the fact that it's working. Now if I change that frequency to say 500 megahertz on the test set, and then it'll move with it, obviously. If I put in 10 megahertz for example, let's move to 10 megahertz, so it's moving with it. It's same if I put in the TX frequency itself. So if we say put in TX frequency, and then let's say 400 megahertz, and then we've entered that in now, so I'll tune to 400 megahertz, in other words put a frequency in a 400 megahertz in, and then it should show an offset. It says it's 1 kilohertz off frequency, So I think this test set will need an adjustment of the reference oscillator to get that back onto frequency. A reason for that is because my test equipment is locked to an atomic frequency standard, a rubidium frequency standard. I also have an off-air standard backup, which comes from the time signal, a time clock from Germany, which is a radio-based time synchronous standard, frequency standard. So I can compare between what is a rubidium atomic frequency standard, a GPS standard, and also a off-air frequency standard as well. And I basically started on the off-air frequency standards to lock all the test gear up to anyway, but then I progressed on to a rubidium and a cesium frequency standard. And there are GPS standards out there. They all have different parts per million accuracy. So we'll need to adjust this here to the right frequency, because it's off frequency at the moment. Just slightly off the reference oscillator in here, the crystal oven, to 1 point something kilohertz offset. So that will be part of the adjustment and checks that we'll be doing next. But that seems to have cured it. Now, to verify that, if I remove the RF now from the input port, so we're not getting any signals and no interference, if I just go to the help menu, select self-test, and we should be able to see it do its thing. So what I'll do, I'll turn the camera around as well, so it makes it easier to see. So let's have a look. So that's passing. Hope for the low pass, fingers crossed. This is a moment of truth. I'm sure it's doing self-test when you repair them than it is before you repair them. I'm convinced of that. Right. Oh, the phone's ringing, so it's all passed, which is good. Back shortly when I've answered the phone. Okay, so what we've got now is we've got our frequency counter hooked up to the Marconi under test. We've got the RF output on the low power port, which gives us a higher RF level output, 0 dBm. Improves the sensitivity of this frequency counter, because these frequency counters do need a fair bit of drive in order to you know, get them to work. But what we've done, we've inputted a frequency of 300 megahertz to measure the offset, in other words how far off frequency we are. One of the things that I forgot to mention is at the back of this unit, round the back, we actually have a coaxial cable connecting in the back, and this coaxial cable that's down here that connects in, it's switched on the back to external frequency standard, because we're actually what we're doing is we're actually inputting an external frequency standard from a rubidium atomic frequency standard, which is highly accurate. And as I said earlier in the video, you can use different off-air frequency standards, for example, which I'll show you one a bit later, that's quite cheap to buy, that uses an off-air atomic frequency clock from Germany in my case, and it receives that signal and then produces then an accurate reference output, which then can be connected to different test instruments to obviously keep them all on the same frequency and accurate all the time, because obviously the internal oscillators wander off frequency if they're not kept in check. So what I've done with this frequency counter, this goes up to 26.5 gigahertz. This is obviously a very highly accurate frequency counter with many digits resolution on it. So I've entered a frequency in, because one of the features on this frequency counter is you can not just only read the frequency directly and then try and adjust something to that frequency, but you can enter an offset by this key here. So I've entered an offset of 300, well, I've entered the frequency that I'm wishing to measure at 300 megahertz, and then we're going to connect this now to the front of the radio test set, and it should pick up the signal and tell us how far off frequency it is. So we are actually quite close there, around about 190 something hertz off frequency, because obviously that's the 0.1 kilohertz. So looking about 200 hertz off frequency. Now there is an adjustment using a trimming tool, which we can use in the test set for adjusting the frequency accuracy. So, and that is this little blue pot here on the CRT board. The reference oscillator's down there on the CRT board. So if we just put the trimmer on that pot there, and then we just very carefully just adjust it slightly. Obviously if you go too wild with it, it starts going way off like that, you see. So we'll just start to tweak it down a little bit, just leave it to settle. This frequency counter does down to 1 hertz resolution as well, so it's quite a very high frequency accuracy. I've chosen to use this just as an example to people watching the video, that you can still use basic test equipment to carry out quite accurate measurements, providing of course it's locked to an external frequency standard. And obviously, the importance of calibration can't be emphasized enough, that you've got to have test equipment that's properly on frequency and outputs the correct levels as well as frequency accuracy, in order for it to be a successful operation. When it comes to using test gear, it's got to be on frequency. Near enough is not good enough, as I say. So now we're down to that. It's also a good idea as well, if you're doing any measurements like this, that you leave things to be stable. And I'll just take my trimming tool out now, because the test set really needs to be on, that the device under test needs to be on really for, I would say, a good hour, for it to get to room temperature, for it to warm up internally, for all the componentry and oscillators to settle down and burn in. And then likewise with any test instrument that you're using with it as well, to measure the frequency accuracy of the output, that again needs to be on, I would say, for at least an hour, even if it's locked to an external frequency standard, because things have got to settle, got to run in, and it's got to be in a warmed up state, so that everything's at the right level, temperature, frequency, everything's all correct. So we've done an adjustment. We just leave it for a little bit to see if it settles, and then we can do micro adjustments after that. But I mean, we're reading there between, that's 4 hertz, 10 hertz, 21 hertz, 22 hertz of frequency, so it's very, very close. The spec for the test set is obviously to try and get it as close as you can. I think in the manual it said something plus or minus 500 hertz, something like that, or as near as damn it. But ideally you've got to, the test set's designed to be accurate to so many parts per million, and so the frequency accuracy is within a certain tolerance, which is in the service manual, but that's well within that tolerance. It's very good accuracy is that, at 30 hertz off frequency now, at that frequency at 300 megahertz. So it's very important when you're doing calibration that you get things done properly, that you make sure that all your test gear and everything's all hooked up to an external standard, and therefore you're going to get those accurate measurements. So that's the idea about frequency standard and calibration procedures, is that you've got to use a known good reference. Otherwise you're starting from an unknown point. So this is why you've got to emphasize, you've got to have an off-air sort of standard, or at least, which is quite cheap to get. So I'll show you that next. So this is an off-air frequency standard. This is what I actually started out with many years ago, about 20 years back. because at the time I think rubidium frequency standards and cesium frequency standards were just simply massively expensive. Many thousands and thousands of pounds to buy, and well out of my budget limitations back then. You know, back in my late teens, early 20s, when these first, well, when I started into doing RF work and test gear. Now, the thing is with this, I think I bought this from RS Components. I don't know if I still do these, but basically there used to be a transmitter here in England, in Rugby, in the Midlands, that transmitted the time signal. And I think the site was owned by the BBC at the time, and they got rid of the transmitter there, and it went to Germany. I think the German people took over the transmitting of the time signal. And so on the back here we've got an HF antenna on the back, which is built into this ferrite rod or whatever. We've got all sorts of little things here. We've got an external antenna that you can connect to that BNC, or you can go on the internal ferrite rod antenna. There's an options output, and then also there's here a core output frequency, and then the frequency there which it receives from the off-air transmitter. And the thing is with these is that quite easy to operate. They give you a choice of three frequency outputs, being 1 megahertz, 5 megahertz and 10 megahertz, which a lot of test equipment can accept. In addition to that, there's you've got the RX supply DC on and off, and then when it settles down and it gets into a state where it can produce an accurate frequency, then this needle will go to the end there once it's sorted itself out. You've got the RX signal, so as you can see, as you move it that way, it's getting full signal. Move it this way, the signal almost disappears. So you've got to put it somewhere where you're getting an end stop signal like that, and then you can go over to check the supply voltage internally should line up with that marker, and then lock. That should be way over as well. And there we are. So it's locked now. Just took it that little bit just to get to the right state where it could lock, and then it'll be producing an output frequency now from these three sockets. So that's now receiving a time signal from an atomic clock elsewhere in the world on HF or very low frequencies, picking that up off the antenna at the back in this case. I mean, obviously in this context I'm using the antenna at the back, but and you've got to move it in the right position in order to get the full signal. But as you've seen, there is a socket on the back, so you can put an external antenna up outside, and then you can put this anywhere you want. So these were fairly inexpensive, and that's the RS part number there, 614514 was the original stock number. I don't know if it's still stocked. Might still be that they sell these, I'm not sure. But it's an off-air frequency standard. So that was my introductory a piece of equipment really into doing test and measurement, making sure everything was accurate. And it's just as good as any other frequency standard I've ever had, to be honest. Nowadays, of course, there's GPS frequency standards, rubidium and cesium frequency standards are readily available now, even on the second-hand market, and very cheap. But back in the day when I was getting into this stuff, there wasn't eBay or Amazon, and there wasn't any way of getting hold of some equipment apart from at Radio Am rallies and Amfests, and even then it needed fixing or it needed to be aligned anyway, so there was always that uncertainty. So if you wanted to buy a genuine rubidium frequency standard or cesium standard, you had to pay many thousands of pounds to get one, which it was just ridiculous. So this saved me a lot of money, and it was very good, very accurate, and obviously it's, you know, originates from an atomic clock to start with, so you know it's actually a very accurate instrument to use. Right, we'll move on to the next phase of putting the test set back together. Okay, so this is the add-on bit at the bottom, which we're just about to put on, the 2957 I think it is, 2958, that's it, that's there. This is a cellular test interface, and inside it just looks like this with the software EPROMs here. for TACS signalling, and then you've got the encoder decoder TACS signalling boards, power supply section in the back. It's also got measurement capability of measuring DC current and voltage through the back here as well, which is quite a useful feature as well. And then there's various interfaces on the side, serial port and disk drive for an IDE disk drive, an old style one. And they did different versions of these. They also did the 2960 version as well, which had additional software in it for trunk radio systems, paging, as well as cellular, and there were various telemetry signaling options as well that you could put in for different telemetry standards for checking various things on different radio system networks. So this was quite an expandable piece of kit, and I do remember having quite a few of these over the years, but I've got rid of them all as time's gone on. But you could basically emulate MPT1327 Trunked radio systems, NMT modes. You could also some of the European cellular standards that were around before, ETACS, that were used in, say, Norway and Denmark and Germany and places like that, use different signalling standards. I think as well there was a CDMA version of it too for the United States. There were various other, you know, connotations in the software that you could get. So we're going to connect this up, and then we're going to do a full test again with this unit on as well. Okay, we've got it all back together now, ready to switch on and do our testing. So first things first, we'll switch on the top unit before we demonstrate the cellular side working. And we'll just go to help, then self-test, and we'll just run the self-test. And if I can press the right button, and then we'll run it through that first just to make sure it passes everything as it should do. Then we'll switch the cellular bit on and demonstrate that as well. So just running through that test now. Fingers crossed it all passes, and then I can ring the guy up who's let me have it to repair, and give him the good news that he can come and collect it. So it's just going through those tests, all passing so far, touch wood. Yeah, this is the final test, I think. Passed, all passed, that's good. Right. So to get the cellular on, once you've switched the power on, you switch this on first, and the 2955 light will illuminate. Then you can go into what is this mode here, right in the middle, which is this CTS mode. And when you do that, then it will go into doing the cellular. You have to have these two connected at the front, or these two connected together and those two connected together. And then what happens is you have to have the IF output from the top bit connected to the bottom bit. There's a coaxial cable at the back and the GPIB cable at the back. So it's just going through its calibration procedure. Now TACS and ETACS used a system called Manchester coding, which was the way that it could hand off to different radio channels, page mobiles, and also change the RF power levels on, which is what you can hear now. That's Manchester coding. And that was designed to, you know, say to a mobile, right, change from power level 0 to power level 7. Power level 0 was a maximum RF output power a cellular mobile would produce, whether it was a handheld or a fixed mobile in a vehicle or that kind of thing, like a transportable thing. And then on the handhelds, power level 0 was like roughly about 400 to 500 milliwatts maximum, whereas power level 7, because it went up in 7 power level steps, went down in 7 power level steps, should I say, down to about 5 milliwatts. So it all went on RSSI levels, and if a cell phone tower picked you up quite strongly, it'd drop your RF level down a bit, so that frequency could be reused in alternate cells elsewhere geographically, and that you wouldn't interfere in the neighbouring cells or the cells that repeat themselves every so many miles geographically. So yeah, that was a way of being able to prevent you know, bleed over between cell sites, because the frequencies that we used were reused again elsewhere in the cellular network, but maybe 10, 15, 20 miles away. But in the peak of a summer, when a mobile was transmitting on about 830 megahertz and receiving about 917 to 960 megahertz in that frequency range, skip used to carry the signal a lot further, so you could interfere with other mobiles in other cells in peak summer conditions, depending on what the sunspot cycles were like. And so what they did, as part of the ETACS tax standard, they had what's called Supervisory Audio Tone, or SAT, and there was different frequencies depending on, two different frequencies if I remember, but you just heard the SAT being calibrated initially when we were dealing with the initial calibration procedure here, and that tone was a supervisory tone that had to be transmitted. It's a form of CTCSS. The mobile had to transmit it, as well as the base station. You couldn't hear it on the call because there was an audio filter in the phone to prevent that from happening. But basically what happened is that without that SAT tone, it wouldn't receive any audio in both ways. So it was a form of CTCSS, or DCS if you want to call it that. More like CTCSS, but just a higher frequency. So that SAT tone had to be present, and what that did, different cell sites use different SAT tones. And so if you had a neighbouring cell 20 miles away and somebody was managing to bleed through into your cell site that you were on your frequency, because it was being reused, although the RF signal could make it that distance in certain lift conditions at peak of the summer months, for example, or if that person went up a high hill, a mountain, or on the moors, you know, over the Pennines, for example, and the signal propagated a lot further than it would do, say, in a city centre area or a town centre area or a rural area, then it could be picked up quite easily on other neighbouring cell sites, maybe 10, 20, 30, 40 miles away, depending on how much power these mobiles used to do. Don't forget, this is in the days when it was quite typical for a car phone to transmit at over 10 watts RF on, you know, on high power. It was as much as 15 to 20 watts in some cases. The cell phone towers themselves used to transmit at well over 100 watts. I mean, it's different today. Cell phone technology today works on such small RF power levels, whereas back then there were really serious output powers. You know, they weren't like the little things that we've got today, and so these were transmitting at quite high levels of RF power. So it was quite easy at this frequency at 900 megahertz for the signal to propagate further. So we'll have a listen now to cellular and on what the control channel sounds like. And this particular mode has basically you can have a full auto test, so you can connect a phone to this device. That's what this bit was made for at the bottom. You had a jig that connected your audio in and out for your mobile phone into here. You had the RF connection, then you had, like, it was an ATE environment, so you would follow the auto test procedure and it would test all the phone. It would send a page signal to it, would check the phone could register with the network. It would then page the phone, it would call the phone, you would test all the DTMF tones, it would check the SAT, supervisory audio tone. It would then check the transmit power levels on power level 0 to power level 7. So it would send that, like, cricket sound that you heard, that Manchester code, to turn the RF power levels down in steps and turn them back up. And they all had to be in certain limits of power, and if they failed, the phone had to be fixed. And back in those days, it was component level repair as well, because I remember having to fix them. And there were only two networks back then as well, Cellnet and Vodafone, or Vodac as it was known as, Raycall Vodac. So this is going back to 1980s now, obviously, but the phone manufacturers back in the day were the main companies in the world who were far bigger than Apple are today. Were Ericsson, Nokia, Motorola had a big foothold in the market worldwide, and they were all massive manufacturers long before what we know today as being the big players in the market like Samsung and Apple. They were just, you know, just not heard of back then, really. I think Apple was still doing Apple Macs, I think, back in 1980s with the clear backs on them so you could see in them. They were not even in mobile phones at all. So, and Samsung made televisions, I think, or food mixers. So there were no involvement in the market. Your big players were Ericsson, really. Ericsson, Motorola and Panasonic, Nokia. They had a massive hold on the market because they also made the mobile phone base station transmitters, or the BTSs, transceivers. So how the world has changed. So yeah, under manual test, so you had full auto, go no go test, so you could test each parameter individually. And what it used to do, it used to test on different channels as well, from the low frequencies to mid, high frequencies, and it would do all these RF tests, receiver sensitivity. It would wind the RF level down automatically and check that the signal to noise and distortion met the right parameters, and it would give you a pass or fail, and it print it out at the end, and that's what you had to give a customer when the customer came to collect the mobile phone after it had been repaired. So, you know, there was no getting out of trying to fiddle with it. You had to pass the test, or you had to fix the phone, and there were devils to fix. Some of the phones, the very small Nokias and Panasonics, were a hell of a job to fix sometimes. So yeah, so I'll set up a test now with the radio test set, and let's hear some what the control channel sounded like and the Manchester coding. Right, so we've set up the we're now back in manual test. This is a manual test mode, which we've got here. So we select manual test instead of auto test. This now is emulating a cellular network, so it's doing exactly what this cell phone base station will be doing. We transmit on channel 323. Well, we can see what frequency that's on by pressing the 2955 button here, and then it gives us a frequency of what. Ignore that transmitter frequency, that's just random at the moment, but this frequency here, 943.0625 megahertz, is what we're actually transmitting on, what signal we're generating, if you like, coming out the test set. So what I've done, I've got it set up now so that on the other test set we're coupling the RF signal out, because the generator's generating that frequency, to this test set. And this is what the control channel used to sound like. So that's that. Now, we're generating FCC forward control channel here, and if we change the mode, if you listen carefully to the data that's been sent, you'll hear it change. So we'll select registration. Data off. That's dotting mode. FCC again. Well, if you change channel, set to 324, 324, enter. You can move to channel 300, for example, and that's it, it had gone, it had hopped off. So we're back again. These are some audible tones, so you could change those to different frequencies, and then you could change the level, data level, and such like, so you could do all that. then you could analyze data as well, so what you're receiving back from the mobile, as well as any DTMF tones, SAT tones, they were all there as well. Now if I just go back, and then you did a full auto test, this is what it looked like. So you had set up all your mobile information in there, what network you were on, and then you do start test, and then it'll basically, so now it's trying to get a mobile to register. Obviously we don't have a phone connected, but that's what that data is now asking it to do. And then it would come up with the easy number. Well, it wasn't called the easy number, was it? What was it called now? Wasn't the IMEI number either. It was another number, I can't remember the name it was called now, it will come to me. But it was long before, you know, IMEIs and GISs and Tampa numbers and things like that. It used to come up with the mobile phone number that the radio would use. So it's trying to page it on different frequencies now, and then it'll fail. It'll say fail, not registered, and that's what it'll do. So you could do all sorts with the testing, you know. And there was a phosphor weighted filter as well as the 2955 mode. So you could pause that. Took it a while for it to respond because it's quite slow. But yeah, so that just gives you like a little rundown. There we are, look. It says manual test abort. It's a fail, no response, you see. So now abort testing. So to abort testing, you'd have to press RTS, which is this button down here, and then go back to manual test again. And so that's what you could do. So I think you could change your AF path as well with different modes. So it's quite fully featured. And in this particular context, if ever you were to get an old 1980s cell phone, then you would basically connect that up to this test set, and if you could power it up, it would work with the test set. And you would just have to then go in and put all the, I think you pressed both buttons in or something. I seem to recollect there was a mode you could get into, that was it, both of them on. You could connect up to it and enter in the details in there. There was something that you pressed and you had to then put in the network details, the network parameters for Cellnet or Vodafone at the time, but I can't remember how you get to that unless you keep your finger on it or something. There was like a secret button press that you had to do, and it configured it so that it would work on a different network. You could enter in all the details of a network, like the country code, what control channels it used, and what its base frequency was, its TX and RX base frequency for that network, because obviously this is in the days when it was a analog cellular network. And I think it may have been in full auto test, and then because we've got here control channel, they're the frequencies, SAT tones, min mobile identification number, that was it, and change format, I think it was, that's it. And that's where you could then go in and enter your system parameters, mobile parameters, display format, test sequences. And then you had a second page, page 2, printer GPIP miscellaneous, I don't know what's in miscellaneous, DMOD source. So you could go into quite a bit with it really, but under page 1, system parameters, that's where you set up your network, your area ID, your control channels that use your voice channels, what channels they, initially TACS was channel 1 to 600, ETACS was channel 1 to 1329, handoff, SAT frequencies, and then there was also mobile parameters. So there was different classes as well, mobile number, so you could then put the phone number in, the target ESN, electronic serial number. It was called an ESN number. You could put that in, and as well you could put the mobile phone number in and then change rate, whatever that was. I'm not sure what that was about. I think it was something to do with billing or something. Display format test sequence, and then it says brief testing select. DTMF is enabled, disabled. Hook flash is disabled. That again, that's where when you put the handset down, it will then clear the call down. So you could set the hook flash to do that as well. So yeah, there was quite a bit to it. You know, it was quite a fully featured little test system. So I hope you've enjoyed it, and I will just do some conformance testing on it now, and then hand it back to the customer. Right, now we're into conformance testing. First of all, we've got the Aeroflex spectrum analyzer set up. We've got it set for channel power mode as well, which is what it's displaying here in the bottom section. And we're just checking the low power output port now on an input port on the test set. We've got a level set -20 dBm at 300 megahertz, and as we can see there, we're recovering that same level here. And likewise, if we adjust this down to say, or we enter a frequency in say -50 dBm, and then we should be getting about -50 there, which we are, channel power. So that means the attenuator is accurate, the calibration of the, I mean that's -67.2 dBm it says, and that's nearly enough, -66.5 roughly. But again, very accurate, no problems there. So that low power port seems to be working fine, and we can test that through the entire range, -70, -80 something dB now, and it's in the noise floor on the spectrum analyzer. Coming back up again, and we can see quite clearly there the levels -27.8 dBm, and we've got -28 there, so that's okay. It's well within tolerance, and that's -20 dBm. And then we keep going. That's 0 dBm there, so that's what we've got there, because we've obviously got to factor in the cable losses as well going to there, so nearly enough a dB loss there, I would have thought. So we'll move back onto this port now, and we'll check this port has the right power level. Again, -20 dBm generating coming out on the SIGGEN at that frequency. We'll do this test as well, I'll do it off camera, where you do the low frequencies, middle and high frequencies, so like 10 megahertz, 300 megahertz, say 800 megahertz, then a gigahertz, that kind of thing. And that's how we normally check that sort of level as well. So that gives us an idea of conformance testing insofar as signal generator output reliability is concerned on both ports, because sometimes you find somebody's fed power up here and burn the attenuator out, so when you switch over to this port that it doesn't quite give the right output level. But as you can see in this case, it's perfect. So that's something to watch out for. Now under channel power, if I go to measure mode and then we go to frequency, and I say put 100 megahertz in, or let's say 100 megahertz, and I change the frequency on here, RX, I've changed frequency 100 megahertz, and then we can check the level again. So we can then go to measure, and then we can do channel power again, -20 dBm, and we're generating -20 dBm as well at that frequency. So I could then go and change that RFGen frequency now, RFGen frequency to 1000 megahertz or 1 gigahertz, and then we could then do the same again. We could then put the frequency in as 1 gigahertz, and then we've now got a frequency of 1 gigahertz minus 20 dBm, and it's saying there minus 21 dBm, so it's 1 dB off, which is equate for what we've got with the cable at that frequency to gigahertz. And likewise we could do it at 500 megahertz for example, and then again set the frequency up to 500 megahertz, and again we've got the correct level, minus 20 dBm. So that just shows you that obviously when you do you change the levels as well, or increments, and then check the levels on there as well. So you could enter minus 30 dBm, and then we're getting that there as well. So that just shows us how accurate it is. Next thing I'm going to do is conformance testing with the 2955B as a reference instrument on top for transmit power audio tests, for the oscilloscope, for mod meter levels, things like that. That's what we'll do next. So we've got the SIGGEN on the 2955B producing output signal into here. We've got a mod level set up at 1 kHz tone at 1.5 kHz FM deviation. We can check that there, and as you can see it's reading 1.5 kHz deviation, so that's within spec. We can check the bar charts as well, hold, various other things, scope, bar chart, which is the button above the scope, so we can check the bar charts are reading 1.5 kHz, which they are. In addition to that, we can also do some other testing as well, which I'm going to be going into in a moment, testing more widely the scope and the mod gens, etc. But at the moment we're just checking what's coming out. The top test set matches what the bottom test set says. So we're generating that frequency in, we've got the audio level there, it's demodulating. Now I'm going to check the AM mode. So on here I will do RF gen mod level or frequency, set mod level, and then I'm going to put 60% modulation on. So we're going to AM now, and then I want to be able to check that this reads AM okay, so I'm going to adjust that now, so we're reading AM, and then I want to make sure that that reads correctly, 60% mod, and I'll just get the transmitter to tune again, and let's see whether we get that modulation depth there, which I think is due to the fact that it's down to the RF gen level needing to be increased. So if I do TX frequency 300 megahertz, so it can do a proper tune, and there we are, we're coming down to 60% modulation, so that's good. So it proves that, and if I change the top test set now, we'll set mod level, and we'll set it at 40% modulation. That's now going to reduce to 40%, which is correct. So that means the AM side's working fine. I think we'll do 10 rads now. So we've got the rad setting, so I'm going to change this now to rad on here, and then we should be getting 10 rad there, which we are. So that's working. So the three modes of FM, AM and rads are all working, so that's good. The next test is to do the audio measurements next.